So why do we call it validation in the first place? It's because we're using the validation set to make choices during learning. This is a very important distinction. Recall from before we were trying to choose the optimum amount of medicine or regularization to take to have a good fit for our target function. If our validation set is similar to the test set, we might be able to choose from all of these different values here and pick out the right one that is going to help us get a good fit for the target. However, we need to be very careful. When we do this estimate of the test cost coming from our validation cost is no longer really a good estimate because it's been used in the tuning. We have to say it becomes a validation set, hence the name. Now you might think that we're splitting hairs here. We know that the test set is unbiased, and in some ways the validation set is unbiased too. We're actually not using it when we're training our model. But we made some choices based on the validation. So, do you think that makes the validation set have an optimistic bias or a pessimistic one? Think for a moment, and we'll come back to this when we look at what's in the light green box below. Here we're saying we have two hypotheses, H1 and H2, that have the same test cost estimate of 0.5 chosen on a uniform distribution between 1 and 0. So they're equivalent with their expected value of the test cost. Now we're going to pick which exact hypothesis to choose for our model, either H1 or H2, by virtue of its actual cost estimate. We're going to take whichever one does better, either the J1 or J2. Now we have a question. What then is the expected value of J? Well, if you think about it, both of the cost estimates have the same value of 0.5 for their test cost estimate. But they also have a variance because it depends on exactly which sample we picked. And that means their actual J1 and J2 have a range, depending on the variance. We only need one of these points to be lower than 0.5 for us to take the minimum, and for that minimum to be less than 0.5. So we can see indeed that the expected value of the cost would be less than 0.5. And because the original estimate of each of them separately is 0.5, this would lead to a optimistic bias. How does that affect us? Isn't it nice to have an optimistic estimate of the test cost? Well, no, because we need it to be accurate, not optimistic. Let's take a look at this in even more detail, with the idea that we could use validation data more than once. Here we have the idea that we're going to have several different models. Let's say we have up to capital theta different models that we want to try out. We want to audition them to find which one is the best model parameter and use that in our actual selection of what we are going to do. We can follow the same type of idea as before and use the training data and split it up so that we have a train and a validation part. And for each validation part, use just the training portion of that to learn a H- hypothesis for each particular parameterization. So for example, for H1 here, and train that model on just the detrained part of size m-k to get H1-. Then using the Dval data set of size k, we're going to get a cost estimate for the validation cost based on this hypothesis. We're going to look through all of the validation costs coming from all of the theta models that we could choose from. And pick, just like we did on the last slide, the model with the smallest cost. and we'll return that as our final hypothesis. It should be clear that there's one particular word in this that makes a lot of worry, and that's this word here, pick, because we're going to induce bias. Our cost estimation coming from all of these validation costs are no longer going to be very accurate, because we have the capability of now selecting from all capital theta versions of the models. Let's check our understanding. So we selected the model theta star, the optimum one, using the validation data set. We can think of validation as training among all of the sets of capital theta models. So we know that the validation cost is actually an optimistic biased estimator of the test cost. So looking at the curves over here, let's have a quick quiz. First of all, which curve is the validation curve? There are two curves here, one to mark the test cost, J-test, and one to mark the validation cost, J-val. The second thing is, why are these two curves going up? And finally, why do you think all of these curves get closer together? So let's try to put all of these factors together. We've had different types of cost estimates. First, the training cost, the test cost, and we've introduced today a validation cost. When we create these costs, we're trying to get an estimate of the ultimate unseen test sample costs. These can be deceptively optimistic biases when we look at how much those points have been used to construct the learned hypothesis. For example, of course, the training data is totally compromised. This is because it's been used to construct the learner in the first place, so we wouldn't use the training cost as a proxy for the test cost. We definitely can use the test set directly because it's totally clean. We separated the test set before we even did the training and validation. The validation set is somewhere in between. We didn't use it to set the model parameters, but in many cases we used it to choose between different models. We can think of this as choosing another set of parameters on top of the parameters. And we're going to say that those are things that we can choose but might slightly contaminate the data set. We'll call those parameters of parameters hyperparameters. When we go to neural networks, you'll hear about this a lot when we talk about hyperparameter tuning. We've seen a couple cases where we have parameters like that, such as decay and k nearest neighbors.